Hello, everyone. My name is Evan, and I'm one of the Algo TAs for this semester. And today we're going to talk about some basic probability concepts that you might need on homework 9. So a lot of this you should have learned in CS 2800, or if you took another probability course like Math 4710, EC 3100, ENGRD 2700. All of these courses should have given you some of the probability tools that you'll need, but of course those aren't formal prerequisites for this course. So we wanted to go through some of the basic ideas you might need for this homework. So here's a general overview of probability, which should be a reminder from the last course that you took in this subject. We can construct a probability space as some set of distinct outcomes. And so probability theory is very reliant on the foundations of set theory. And we call this probability space a sample space. And so an event is some subset of that sample space. So we have this set of distinct outcomes, and we take any subset of those outcomes, and we call that to be an event. So let's consider a sample space where we roll a dice. We have 6 different distinct outcomes, right? The numbers 1 through 6 can appear. And the event A, we can say is, the dice rolls that are even, right? Because that's a valid subset of our sample space. And that event consists of 3 out of the 6 possible outcomes, right? 2, 4, and 6 are valid outcomes, which is a subset of our sample space. And so when we're thinking of events as sets of outcomes, then the probability that A and B happen, or the probability that we have 2 distinct events that both happen, can be denoted as the intersection of 2 sets. And so pictorially, we look here, and we see that the probability of A and B is represented as the intersection of these sets. And the probability that at least one of 2 events happens, either A or B, is the union of 2 sets. So we can just draw that here. And if we know that A and B are disjoint, for example, let's say we have some probability space that looks like this, where this is A and this is B, then we could say that the probability that A or B happens is just the sum of those 2 probabilities. And so this leads us to an idea that we call the union bound, right? And often while we design randomized algorithms, we want to place a bound on the probabilities that at least one event occurs without necessarily knowing the exact probability. And even if we don't know that the events are disjoint, we can still usually place an upper bound on the probability using the union bound. So one way to do that is by saying that, well, if the events weren't disjoint, then we would have to subtract out the probability of their intersection, right? Which means that we'll always be upper bounded by the sum of all of the probabilities, regardless of whether they're disjoint or not, right? So this leads to this inequality here, which is, again, more formally called the union bound. And you can also see this more visually through the inclusion-exclusion principle. So now let's talk a little bit about conditional probability. We use conditional probability to model how the probability of some event changes given that we know about the occurrence of some other event. And so more formally, this can be said as the probability of A given B is equal to the probability of A intersect B over the probability of B, right? And let's look at this a bit more visually as well. Suppose I have this probability space where this is A and this is B. And I apologize, my drawing isn't the greatest. Well, if we know that B happened, then that restricts the possibility of other events to whatever B is, right? Like we can't have any event that's not in B occur. So then now the probability that A occurs is going to be whatever is already covered in B, right? Because our new sample space effectively becomes the right circle. And so we can use this to calculate things like what is the probability that we land 3 heads in a row, given that I've already flipped one and landed a heads, right? If I didn't know that I already rolled a heads, or I already flipped and got heads, then I'd have to calculate the probability of 3 heads landing in a row. But now I only need to calculate the probability that 2 more heads land in a row after knowing that the first one is a heads. From this kind of general intuition, we can also derive Bayes' theorem, and we say that the probability of A given B, and that's how we read this vertical bar here, it's A given B, is equal to the probability of B given A times the probability of A over the probability of B. And this should be familiar from your basic probability courses. And usually when you're doing this computation, it's helpful to break up the denominator. So we could write something like the probability of A given B is equal to the probability of A times the probability of B given A over the probability of A times the probability of B given A plus the probability of not A times the probability of B given not A, right? Because A and not A, or A or not A, consists of the entire sample space. And so we can condition on whether A occurs or not to get back the probability of B, essentially. And this is called the total probability theorem more formally. So now let's talk about the notion of independence. Intuitively, if two events A and B are independent, then the fact that A occurs does not change the probability that B occurs. So we can write this as probability of B given A is equal to the probability of B. And equivalently, you can derive the fact that if the probability of A and B is equal to the product of the probability of A times the probability of B, then this also implies that events A and B are independent. So for example, you can consider a series of coin tosses that are independent, right? You could also consider when A is 2 dice rolls adding up to 10 and B is the first dice roll equaling 1. Are those two events independent, right? Independence is very different from events being disjoint because disjoint immediately implies that the events are not independent, right? If the events are disjoint, then the probability of A and B is 0. So it cannot be the probability that the probability of A and B cannot possibly be the product of A times the probability of B, right? It immediately implies that the two events are not independent. You know for certainty that if one event occurs, the other event cannot occur. Okay, so now let's talk about random variables, which help us kind of put a little bit more generalization on these ideas of events and subspaces. So random variables are just a way for us to assign values to different outcomes in a probability space. For example, let's say our probability space contains the outcomes of a dice roll. We can let some random variable x represent the value of the dice roll. So if x is equal to 1, that's the outcome that occurs when the dice roll is 1. And if the space contains the outcomes of the dice rolls, how about 2 dice rolls? And y represents the sum of the pair of those dice rolls. And we can say that y is equal to 5 when we have any 2 rolls that lead to y equaling 5. So how about 1 and 4, 2 and 3, etc. And we can call a special type of random variable an indicator random variable for some event A. And indicator variables are automatically set to 1 if some event has occurred and 0 if it did not occur. So hence we have the probability that I sub A is equal to 1 is the same as the probability of A, right? Because I just takes on 1 or 0. So here are some common discrete random variables, as well as their distributions, their expectations, and their variances. You're probably not going to need the variance, but it can be helpful to just kind of have a summary of some of the random variables we'll see in this course. So we can extend the notion of independence from events to random variables, right? If 2 random variables, x and y, are independent, then that means that for every value, x and y, in the support of x and the support of y, then the probability that x takes on some event is completely independent of the probability that y takes on some value. So this also means that the probability that x is equal to some value little x and the probability that y is equal to some value little y is just the product of those 2 probabilities. And intuitively, this just means that the value of x can never influence the value of y. So now let's talk about expected value, which is probably the most common, or one of the most common things that we're going to use in probability. Intuitively, it's just a weighted average of all the values that a random variable could take, right? So let's denote x as value of a single dice roll. Then what is the expectation of x? Well, the probability of getting any one number is 1/6. So it'd be 1/6 times the probability, or times rolling a 1. 1/6 rolling a 2, 3, 4, 5, 6, right? And what is this? 11, 15, 18, 20. 21 over 6, I think. Something like that, which is 3.5. So expectation is also a linear operator, right? If I can write a random variable y as a linear combination of other random variables, then suppose that y can be written as y is equal to ax plus b, then the expectation of y is just equal to a times the expectation of x plus b. It's also helpful for when I can say the expectation of x is equal to, let's say that x is equal to y1 plus y2 all the way up to yn. Then I can say that the expectation of x is equal to the sum, the expectation of yi. And this is true even when the individual y's are not independent, right? And so similarly to how we calculated the expected value of a single dice roll, we could come over here and calculate the expected value of the sum of 2 dice rolls. And again, indicator variables become very useful because if x is a number of heads and 5 coin flips, we can represent x as a sum of 5 indicator random variables. Okay, so let's consider a fair coin that's tossed repeatedly and independently until we get either 2 consecutive heads or 2 consecutive tails, right? Well, we know that after the first toss, the probability that the next toss is the same as my prior toss is just a half, right? The first toss was a heads, so the probability that the next one is also a heads is just a half. So we can denote y as a total number of tosses. And we can say that y is equal to x plus 1, where x is a geometric random variable with probability 1/2. Then the expectation of y is just equal to 1 over 1/2 plus 1, because this is a linear combination of our random variable y, just equal to 3. And here's the answer written up a little bit more nicely if you want to see the same thing. Okay, now let's talk about Markov inequalities. So Markov inequalities are useful for bounding certain probabilities of events that we consider kind of difficult or, a little infeasible. Markov's inequality provides an upper bound on the expected value of some non-negative random variable. So given partial information about its probability distribution, we can say that the probability that x is greater than or equal to some constant a is upper bounded by the expectation of x over a. And we can think about this in the following way. If x returns very large values on average, i.e. the expectation is very large, then it's likely that the random variable x takes on a large value, right? While if the expectation of x is very small, it's pretty unlikely that x will take on some very large value, right? And this comes from the fact that when we're calculating the expected value of x, we had to sum up all of the values in the support of x, right? Where we say the support of some random variable is the set of values that a random variable can take. So it wouldn't make a whole lot of sense if our expected value was really small, but then we somehow found a value that was incredibly large, right? That can't be a very likely event. So here's a formal proof of Markov's inequality, and you don't really need to understand the proof, but this can hopefully help convince you of the fact that it's true. So let's look at some example problem. Suppose we have a coin that's weighted so that the probability that it lands on heads is 20%, and it's flipped 20 times. And so we want to show that the probability that it lands on heads at least 16 times is less than a third. Okay, so we'll denote some random variable x to be the number of heads in 20 tosses. So x is a binomial random variable, and the probability of getting heads is 20%. It takes on probability 1/5, and we have 20 trials. And the expectation of this binomial random variable is just going to be the product, right? It's NP from what we saw on one of the prior slides. So this is just going to be 4, right? And so the probability that x is greater than or equal to 16 is just going to be equal, or not equal to, upper bounded by the expectation of x, which is 4 over 16, which is equal to 0.25, which is indeed less than a third. All right. And let's look at one more problem. So a factory that produces laptops in batches of 1,000 finds that on average, 2 laptops per batch are defective. So let's find a bound for the probability that in the next batch, less than 5 laptops are defective, right? Okay, well, so we know that, let y be the number of defective laptops in the next batch, right? right? We know that the expectation of y is simply 2. And we want to find the probability that less than 5 laptops are defective, right? So we can say that the probability that at least 5 laptops are defective is upper bounded by 2/5, right? So then we can take the complement of the event to find the probability that less than 5 laptops are defective. So the probability that less than 5 laptops are defective is going to be greater than or equal to 1 minus 2/5, which is equal to 3/5. And that's exactly the math we have here. So I hope this was helpful. These are some ideas that you're going to need on homework 9, and along with some of the basics you might recall from calculus or geometry could also come in handy. But yeah, this is pretty much all we really need for now. It's helpful to know, though, that there are other inequalities. Markov's inequality gives a very basic bound, but we also have more complicated bounds like Chebyshev's inequality and Chernoff bounds that we could use as well. But they do come with additional constraints, and so we're not going to require them in this course. So I hope you found this helpful, and yeah, good luck on this week's homework. Definitely come by to office hours if you need help.